All right, so we're just going to continue with our transformations, and the first one we'll start with is reflections. Reflections. Okay, so what is a reflection? So again, as always, let's just let f of x be a function, any function, all right? Okay, and we're just gonna do some transformation to this. So minus f of x what will that do? What happens if I multiply the function by -1? That will do the following. It will reflect the function's graph. It will reflect the function's graph over the x-axis. Okay? And I'm going to show a nice image that shows all this. Okay, and similarly, how about if I multiply the input by -1? So it's f of -x. So notice the difference in the placement of the minus sign. This will reflect the function's graph, but now over the y-axis. Okay. Okay, so in this second bullet point, I'm multiplying the input by -1. Okay, notice the difference in placement of the minus signs. All right, so let me go to my first image of the evening. So let's just get this, copy. All right. Anyways, let's just talk about this. Let me just make it a little bigger. All right, anyways, let's just say we have our original function here in blue, okay? F of x is just this blue guy. If I do minus f of x, which will be this, as I wrote up earlier, you just reflect it over the x-axis, and that's exactly what it is. All right, so this was reflected over the x-axis to get that. That's minus f of x. And also f of -x, as I wrote before, that reflects the graph over the y-axis. Okay, so we just took this guy and we just flipped it over, reflected it over the y-axis, and we got this. Okay, so that's what it looks like geometrically. Okay, so that's the picture. And how about algebraically? What do you do algebraically to get this? So that was geometrically, now algebraically. Okay, first fact. For a reflection about the x-axis, which was, remember, minus f of x. So just in parentheses, I'll just remind you, that's minus f of x. The y values get multiplied by -1. Okay, so that's the algebraic interpretation of a reflection. The y values get negated, or in other words, you multiply the y values or the outputs by -1, and what happens to the inputs? The inputs stay exactly the same. So let me write it, is that the x values stay the same. Okay, and you can see that in the picture here with the vertical reflection. This x value on the original graph is also present on the reflection. It has the same x coordinate. This point and this point have the same x coordinate. All right. But its y coordinate, as you can see, was negated. You can see that from the picture. Okay. And then we have the analogous statement for a reflection about the y-axis. So let me just write that down. For a reflection for a reflection about the y-axis. And I'll just remind you in parentheses, that's f of negative x. The x values. So there's a difference here. The x values get multiplied by -1. The y values stay the same. Okay, so this is the algebraic story. How do you manipulate the actual coordinates themselves? Well, this is how you do it. All right, so now let's apply this knowledge to a nice example. So given the function table, so let me just write out a function table for you guys. We'll have x here and f of x down here. So usually I write these things vertically. I'm just going to write it horizontally right now, just because it saves room. So the inputs, the x's will be 2, 4, and 6. And let me give the outputs to be 1, 3, 7. All right. So I hope we're all comfortable with looking and reading function tables. Okay. Essentially, the output 1 was associated to 2. So 2 gets mapped to 1, 4 gets mapped to 3, 6 gets mapped to 7. Okay, now the question is, give me the function table. Give me the function table for f of negative x. F of negative x. Okay, so would someone like to tell me how can I obtain, so given the function table for f up here, how can I obtain the function table for f of minus x? So would someone like to explain that?
Multiply the x values by -1.
Yes, exactly. Very good. Just as I wrote up here on this fact, for f of negative x, which is what we're looking at, the x values get multiplied by -1. So I go up to 2, 4, and 6, our x values, and I just multiply them by -1. So that's -2, 4, 6. Outputs stay exactly the same. 1, 3, 7. Done. That's it. Oh, whoops. I forgot minus signs here. Yes. Okay. So hope that's all good. Inputs got multiplied by -1. Outputs stayed the same. All right. Nice. Now let's move on to even and odd functions, something very, very interesting. So even and odd functions. So just like how numbers, whole numbers can be even and odd, can be even or odd, we can actually talk about functions being even or odd. Okay. All right. So we're going to start off with a definition. All right. Let me just define what it means to be even or odd. All right. So here we go. Here we go. A function is called even. Okay, I'm going to underline even because that's the word I'm defining in this definition. If f of x equals f of negative x for every input x. Okay? So the outputs of x and negative x are the same. When you apply the function f to both x and its negation negative x, their outputs are the same. Okay? So that's even. How about odd? Next, a function is called odd. So I'm underlining that because that's what I'm defining. If, so this is slightly different, so just pay attention. If f of negative x is equal to minus f of x. Okay, so that minus sign gets pulled out of the input and comes out in front of the function. Okay, all right, example. Okay, prove that f of x equals x squared and g of x equals the absolute value of x are even functions. Okay, so this is the task that is given to you. You're given f of x is equal to x squared and g of x is the absolute value of x, and you are to prove that they're even functions. Okay, so all you need to do is just show that the definition of evenness is satisfied. You need to show that if you plug in f of x, if you plug in x and negative x, you get the same output. All right, so let's do it. First, let's do x squared. So let me examine f of negative x. Okay, by definition, that just means I'm plugging negative x into the x squared function. All right, is everyone okay with how I got that? I'm just plugging in negative x into x squared, but a negative number squared is equal to the positive version of that number squared. That's the same as x squared, right? Like if I square -2, I get 4, and if I square +2, I also get 4. But look, isn't x squared just the definition of f of x? Yeah. So that's it. We have shown that f of minus x through this chain of equal signs is equal to f of x, which is the definition of even. All right, scroll up. It's even if f of x equals f of minus x, and we have shown that through this chain of equal signs. All right, next, we do the same thing for g. Look at g of minus x. By definition, it's the absolute value of negative x. Good, and in a similar way, the absolute value of a number's negation is the same as the absolute value of that number, right? The absolute value of -3 is the same as the absolute value of 3, for instance. And this is by definition equal to f of x, g of x, excuse me, g of x. All right, so observe that in this chain of equal signs, we have shown that g of minus x is equal to g of x, which is literally the definition of an even function. So that's it. All right, and now let's do one for odd. Prove that f of x equals x cubed plus 2x is an odd function. Okay, so for this, we need to show that, let's go up to the definition. Odd is if f of negative x is equal to minus f of x. So that's what we're going to show. So we're going to start with the left-hand side, f of minus x. So here we go. So f of minus x, by definition, is negative x cubed plus 2 times negative x. Okay? Good. This is the same as negative x cubed minus 2x. Excellent. And now what can we do? We can actually factor out a -1 from this. So this is the same as x cubed plus 2x. Okay, so does anyone see anything interesting about the expression in the parentheses? Can someone identify to me what that expression is in the parentheses?
That's our original g of x.
That's our original function f of x that
Yeah.
we started with. Exactly. Good. So the minus sign comes down and the parentheses get replaced with f of x. And observe that through this chain of equal signs, we have shown that f of minus x is equal to negative f of x, hence satisfying the definition of odd. All right. So any questions about these calculations?
So you can't really reflect these, can you?
Okay, right. So the fact that they have this sort of condition, they have a symmetry about an axis, which I'm going to. That was literally my next point. So you can reflect them, and they actually have a very nice property. So that leads perfectly to my next point. Okay, the first thing, even functions are symmetric about the y-axis. And you can see that just by looking at the graph of the parabola of x squared. You can see that there's a nice symmetry going on. If I were to fold over this left side of the parabola over the y-axis, it will land perfectly on the right side. That's intuitively what we mean by it's symmetric about the y-axis. You can fold it on one side and it will land on itself. And odd functions also enjoy some sort of symmetry. Odd functions instead are symmetric about the origin. Okay, and just a quick graph of that. You can look at the x cubed function, x cubed. It looks something like this. And if I fold this part of the graph over the origin, you can kind of see like over the middle point here, it will land exactly on itself. Okay. All right, so that's the geometric interpretation of even and oddness. Okay. Okay, so any questions? All right, so let's keep moving. Next topic. So we're going to finish out our transformations now. We're going to do vertical stretches and compressions. All right. So what does this mean? So again, we're going to be algebraically altering our function somehow. And this is what it is. So given a function, any function, f of x, the new function a multiplied by f of x. So a times f of x is a vertical stretch or compression. Okay, and how do we figure out whether it's getting stretched or if it's getting compressed? Well, that just depends on this coefficient here of a. So it's it's completely determined by what a is. So how does that play out? Well, this is how it works. If that guy a is strictly greater than 1, it's a stretch, okay? The graph is stretched vertically. Okay, so it depends on the nature of this coefficient a. The graph is stretched vertically. All right, and if a if a is between 0 and 1, so if a is in between 0 and 1, that's how I notate it. this is actually going to be a compression. The graph is, the graph is compressed vertically. All right, and that's it. So that's all you need to know. So maybe you're wondering, what if A is negative? Well, if A is negative, it's going to be a reflection about the x-axis followed by a stretch or a compression. Okay, because the minus sign in front of A will cause a reflection about the x-axis, and then you do your stretching or compressing. Okay, so really we just care about these cases. All right, so
But if A, it's like nothing, because if A is 1, like then it's like nothing. So like just ignore it, because like it's just minus, right? Just making sure.
yes, you're saying if A is 1, you just get the function f of x itself?
Yeah.
Or if it's
No, wait.
-1.
But minus like just a reflection, because it's like just 1, so it's nothing. Just want to make sure if it's not a crazy
No,
other thing.
So in the special case that A is -1, you get negative f of x, which from earlier is
Just a reflection.
Exactly.
Okay, perfect. Just want to make sure.
Mm-hmm.
Thank you.
Of course. So I will do a quick interactive thing like I did last class with the slider, just to show you guys how this looks in real time. So let me just share my browser. Just give me a moment. Okay, we're doing vertical compression. Okay. So I hope everyone can see this. I got this graph here. Okay, so here I have this function. Don't worry about it too much. We're going to get into exponentials in a week or so. But this function is e to the minus x squared, where e is something we're going to get to, so don't worry about it. But it is a function, and here's its graph. Now, what I have g of x defined to be, it's a times f of x. And with this slider, I can manipulate g in real time. So if I make a big, it's going to stretch the graph as such. All right. So you can see in real time, as I make a bigger, it is stretching it vertically. All right. So that's kind of cool. And if I make a to be between 0 and 1, like it will be a compression. It will get smaller vertically. And let me just do that. Yeah, so see how it's getting compressed. All right, so that's something cool. And it's just evidence that this actually does vertically stretch or compress. All right. Let me get back to my notes. All right, and we're back to the notes. So here is, right, okay, so that was the geometric picture. That was the graphical picture. Now, what's the algebra? What's the algebraic interpretation? Okay, so in a vertical stretch / compression, the y values get multiplied by a. Okay. X values stay the same. Okay, so that's the algebraic interpretation. The y coordinates get multiplied by a, x value stays exactly the same. All right, so this is very important. Okay, so example. Find the formula for stretching for stretching, f of x equals x cubed. Hold on. By stretching, f of x equals x cubed vertically by a factor of 4 and shifting down 2 units. All right, so we need to apply these transformations to f and get some sort of formula for it. So I'm going to take care of both of them separately. So right now, the order in which I applied the transformations does not matter, but soon it will matter, and we're going to get to that. Okay, so right now we can do each of them in any order we want. So first, let me do the stretching. So this will be stretch by 4. So stretching by 4 is just 4 multiplied by f of x, which would be 4 times x cubed, which is just 4x cubed. So that's the algebraic result after stretching by 4. And how about shifting down 2? Down 2. So this was something from last class on Monday. So would someone like to tell me what I need to do to the function to shift downwards by 2 units?
You need a vertical translation of -2.
-2. And where do I need to subtract 2?
On the right-hand side, which will affect the y-axis.
Right. Okay, perfect. So I just subtract 2 from the function. Very good. That's 4x cubed minus 2. And that will be the final answer. Okay. So as I said, the order in which we do these things, oh wait, maybe it would matter. Okay, so excuse me what I said before when I said the order doesn't matter. It does matter, actually. Okay. Because if I were to do down by 2 first and then multiply by 4, I would get a different answer. Okay. So just forget that. The order does matter, and I'm going to explain the correct order later. All right. But this was the correct order. All right. So I apologize for that. Okay, so that was horizontal stretching. No, that was vertical stretching. Now let's do horizontal stretching. Okay. All right, so this will be horizontal stretches and compressions. All right, so how do we do this? So again, given f of x, the new function, f of bx, you multiply the input by b, is a horizontal stretch or compression of f of x. Okay. All right, now how do we determine whether it's a stretch or a compression? That will be determined by the nature of this number b. So how does that play out? All right, here we go. If b is strictly greater than 1, the graph is compressed. Saeed, your mic is on, by the way.
Oh, sorry about that.
It's okay. If b is greater than 1, the graph is compressed by 1 over b. Okay, so maybe it's not quite what you think. It's actually compressed by 1 over b, not b, the reciprocal of it, 1 over b. Okay, and the same thing. If b is between 0 and 1, the graph is stretched by, again, 1 over b. So this is quite different than the vertical case. In the vertical case, if that number was greater than 1, it was stretched, and if it was between 0 and 1, it was compressed. Here it's the opposite. All right, so very subtle points. All right, we need to pay careful attention to the distinction here. All right, and what is the algebra that goes along with this? So in this case, what do we do to the actual coordinates? The x values are multiplied by 1 over b. 1 over b, not b, 1 over b, right? So that's important. And that's maybe not what you would expect, okay? You multiply the inputs by 1 over b. So this is different than the vertical stretch. All right. Okay, so example, and then I'll go and do the interactive demo with this. So first example, given the function table, so I really like these examples with the function tables because you have to manipulate the coordinates explicitly. I think it's really nice practice. So given the function table, so we have x, f of x. So I'm just drawing the function tables horizontally now, just because they save some room. So it'll be 2, 4, 6, 1, 3, 7. So this was given to us. I want you guys to find the function table for f of 1/2 x. Okay, so firstly, what is b in this example? So I scroll up to horizontal compressions. I have f of bx. Okay, here I have f of 1/2 x. So what number here is playing the role of b? Would someone like to tell me b is equal to what in this example?
1/2.
I heard a few people say something at the same time, so I couldn't hear.
Is it 1/2?
Yes. Yes, Vincent, exactly. Yeah, b is 1/2. Perfect. Good. So b is 1/2, and now look at what I wrote here. The x values are multiplied by 1 over b. So here, the x values are multiplied by 1 over 1/2, because that's what 1 over b is. And what is 1 over 1/2? That's 2. Okay? The x values are multiplied by 1 over b. b is 1/2, so 1 over 1/2 is 2. All right, and that's pretty much it. So we get our function table as follows. So x is here, f of 1/2 x is here. Okay, so the the x values get multiplied by 2. So what were my x values? They were 2, 4, and 6. I just need to multiply each of those guys by 2. All right, so that would be 4, 8, and 12. Y values stay exactly the same. That's it.
Could you just go over how 1 over 1/2 equals 2? If you don't mind.
Absolutely, absolutely. So 1/1/2, we actually are dividing fractions. This is actually the same as 1/1 divided by 1/2. You agree with that? I just changed the 1 with 1/1. And now you just do the keep, change, flip business. You multiply by the reciprocal of the bottom there. So this is 1/1 multiplied by the reciprocal of 1/2.
Got it.
And this is 2. Yeah. So we were dividing fractions in disguise there.
Thank you.
Yep. Good. And that is that. Okay, good. Let me just go and do this interactive demo again. So let me just give me a moment to share my browser. Okay, so we're going to number 5 now. Okay. All right, anyways, look at the function I have. It's f of x is absolute value of x. Hopefully you guys are somewhat familiar with its graph. It was a part of those so-called toolkit functions that I wanted you guys to be familiar with. And look at what g of x is defined as f of bx. So if b is greater than 1, we said it was a compression, which means it's going to get skinnier. And that's exactly what happens. Look at when I make b greater than 1. It actually does compress horizontally. This is a compression horizontally. Okay? And I wrote also that if b was between 0 and 1, it actually got stretched horizontally. Well, look now as I move to the left, it is getting stretched horizontally. Okay? So that's, yeah, so that's the geometric story there. Okay, the y values, let me just make note, are staying the same. It's the x values that are changing here. Okay. All right, cool stuff. All right, so back to the notes. Back to the notes. All right, and we're actually almost done, guys. All right, good. So now we would like to combine all of our previous learned transformations into one. So the next heading, and I think the last thing of tonight is combining transformations. Okay. So we're actually not, so we're not gonna, so we have now introduced all of the possible transformations, and now we're just gonna combine them into some problems here. Okay, so here we go. So given a function f of x, we can apply several transformations to it at the same time. Okay, so this is what it's going to look like in its most general form. Okay, so just don't get scared when I write this. It's really not that bad. So we have a multiplied by f of b times x plus h plus k.
Sorry to interrupt. The toolkit function just really means what? It just means that list of transformations?
The toolkit functions are just very common functions that math students should just be familiar with, and they're also the functions that we're going to apply transformations on very frequently.
Okay.
Just, yeah, so we just want to be familiar with them. Okay, so I just wrote this expression down. I actually have applied all of our transformations at once, okay? So let's just break it down. So A here. A is our vertical stretch compression.
Is this the order or the?
Order's coming. This is not the order. That's coming right next. I'm just identifying what each of these letters do here.
Oh.
So A is the vertical stretch. Next, B. B is the horizontal stretch or compression. Okay, so I know this looks kind of crazy, but all it is just me applying all of our transformations simultaneously to a function f. All right, next, let me talk about this letter H. H, this was from from Monday's class. H is our horizontal shift. And finally, our K, that's the vertical shift. Okay, so I hope now that I have identified each letter and what it does, maybe this is a little less overwhelming. This is just all of our transformations that we have spoken about, just applied at once to the function f. Okay, now, here is the order in which you apply them. Okay, the order. So this is very important. All right, the order. First, you horizontally stretch. That's the first thing you do. Horizontally stretch by 1 over b. Okay, and I'm just going to write down what you need to do. You multiply, so remember with that, you multiply your x values. So you multiply your x values by 1 over b. That's the algebraic interpretation. Okay, so that's the first thing you do when you're given a function with some transformations applied to it. Number 2, horizontally shift by h. Okay, and remember the algebraic interpretation of that? That is just you add h to the x values. So that was you add h to the inputs or the x values. Remember, x values is synonymous with inputs. And y values are synonymous with outputs. Okay, that's the second thing you do. Third thing you do, now you do your vertical stretch. Vertical stretch by A. And what's the algebraic interpretation of that? You multiply y values by A. Okay, and the final thing, this is the last thing you do when you're given a bunch of transformations, you vertically shift by K. And algebraically, how do we achieve that? You add K to the y values or to the outputs. Same thing, add K to the y values.
If you have a reflection, where does that go inside?
So it depends. Reflection about, you're talking about a reflection about the x-axis or reflection about the y-axis. If it's a reflection about the x-axis, that was minus f of x.
Yes.
And if you look, that's actually the same as a vertical shift. Oh, no, I'm sorry, a vertical stretch. So that would go here. And that's a vertical stretch because it's the vertical stretch when A is -1.
So could you first do the vertical stretch and then reflection, or both are okay?
That, yeah, so the order of that would not matter.
Okay.
Yeah.
And the same applies for the
F-
horizontal stretch.
Yeah, so
About
if you do a reflection about the y-axis, which is f of negative x, that is a special case of a horizontal stretch. So you would do that first.
the reflection or the horizontal stretch.
The order in that case would not matter.
Okay. Gotcha.
And that, yeah, so that's good. Okay, so here's the order. Excellent. Now I think we just have an exam. Yeah, so we just have a few examples, and then we'll be done. Okay, so example. So we're going to work again with a function table. This is a really nice way to explicitly work with coordinates. All right. So given the function table for f of x, create a table for 2 multiplied by, excuse me, 2 times f of 3x, close of parentheses, plus 1. All right, so we have multiple transformations going on here. So first I need to tell you the function table for f. So this is just given to you. It's 6, 12, 18. And the bottom row, the outputs is 10, 14, and 15. Okay, now we need to go up and look at our order, okay? We need to first horizontally stretch by 1 over b. That's the first thing. So, step 1. First, so this is just straight from our order that I have listed. You first do the horizontal stretch. So first, horizontally, it's actually a compression in this case. Compress by a factor of. So you take 1 over this b value. So you take 1 over 3. All right. So you horizontally compress by a factor of 1 over 3. Okay. So this means, algebraically, this means we multiply the x values by 1/3. Okay, so our new x values are okay, so we horizontally compress by a factor of 1/3. Algebraically, that means we multiply our x values by 1 over 3, which is the same as just dividing by 3. So I do 6 over 3, which is 2. I do 12 over 3, which is 4. And I do 18 over 3, which is 6. Good? So here are our current x values, okay? All right, so next transformation. What was next in our order? Horizontally shift. This function that I've given you, 2 f of 3x plus 1, actually has no horizontal shift, so we skip it. So we go next to the vertical stretch. Next. Vertically stretch by 2. So we have to look at this coefficient in front of f, and it is 2. So we vertically stretch by 2. This means, so what's the algebraic interpretation of this? This means we multiply our y values by 2. Okay? Just give me 1 second. I'll be right back.
Didn't I do this one already?
Okay, I'm back. Sorry about that. So we multiply our y values by 2. So look, I have the y values 10, 14, and 15. If I just multiply each of those guys by 2, I will get 20. I'll get 20, 28, and 30. Okay? And the last thing on our list, finally, the last thing you do, you vertically shift. And what are we vertically shifting by? Well, we have a +1 out here. So we're vertically shifting by 1. So we're actually vertically shift up. It's +1, up 1 unit. And what's the algebraic thing to do? You add 1 to each y value. From step 2. So you don't go back to your original y values and add 1 to those. You go back to your current y values, which are now 20, 28, and 30. Okay, because if you went back to your original y values, you would be completely ignoring this vertical stretch by 2 that we did in step 2. So you need to add 1 to our y values from step 2. And that's easy. So 20 plus 1 is 21, 28 plus 1 is 29, and 30 plus 1 is 31. Okay, and that is it. So now we just compile everything in our table. So our new function table is as follows. So I have x, and this will be 2f of 3x plus 1. All right, so what are our x values? Well, that was from step 1. We need to go and call upon these guys, 2, 4, 6. And our last y values were these guys. So 21, 29, 31. And that is it.
Can you scroll back to the beginning of the question? I have a quick question.
Mm-hmm.
So would you say like the 6, 10 point moved to the other point, like, or it's just like a new set of points?
No, that's a great way to think about it. The original point 610 got sent to 221.
So it's the same point, just dislocated. It's not a new set of points, right? Just making sure.
It is a new set of points because the graph is going to look different. So the point
Yeah, but like it's the same point dislocated. It's not like 3 other points. Like, I don't know how to express myself. Sorry.
Yeah. So the way I like to think of it about it is that the point. Okay, so 610 was our original guy. 610 got sent to 221 under this transformation.
Yeah, that was the question. Thank you.
Yes, this point corresponds exactly to that point under the transformation.
When you are writing down a what is it? Reflection inside. How do I say this? Hold on. Anytime you are reflecting something over the y-axis where you put the negative, do you want it to formulate an equation? Do you want it outside the parentheses, or we can put it inside? Like we can combine, or you want it outside, like in vertex form?
So you said a reflection about the y-axis, right?
Yes.
That's f of negative x.
Yes. And if you were to formulate an equation, do you want that outside the parentheses, like negative parentheses x minus h, or it can be inside that?
I see what you're saying. It's going to be outside the parentheses.
Mhm.
It's so in f of negative x, that's b is equal to -1 in the horizontal compression. Yes, it's going to be outside the parentheses. So let's go up here. It's going to be outside the parentheses. Is that what you were asking?
Yes.
It's going to be outside, yes.
But can we
Absolutely.
combine that? Like, can we like distribute that in? So for instance,
Yes, okay, right. You can do that, but these set of steps that I've outlined here, the
Mhm.
function needs to be in this form.
Okay.
If you distribute in the b value into these parentheses,
Mhm.
these steps are no longer correct.
Okay.
Yeah. So we're going to do that. We're actually going to do that now. We're going to deal with this problem. Good question. All right. So I think we are, so we're at our last example of the night. And we're going to be touching upon this issue that's Saeed just brought up. All right. So just before I move on, just any questions as to how I got this new table. So there is a nice question like this on homework 5. I think it's the last question on homework 5. It's just like this. All right. All right. All right. So last thing of the night. Here we go. Use the graph of f of x below. So I'm going to pull that for you guys. Just give me a second. Use the graph of f of x below to sketch a graph of this new function, f of 1/2 x plus 1, close parentheses, minus 3. So let me pull up this image now. Okay, so here is the graph of the function that I'm talking about. This is the graph of f of x. So it's kind of just like the upper portion of the unit circle. No, not the unit circle. It has radius 2. So it's just the upper semicircle. Okay, now this is f of x. We want to now apply our order of transformations and get a graph for get a graph of this guy. All right. So there is an issue here. So I'm going to write it first. Firstly, we need to rewrite the input of f of x of the form f of b multiplied by x plus h. Okay? We need to write it as something b multiplied by x plus h. If we look at the way our function, the way it was given to us, it's not of that form. It's 1/2 x plus 1. There's no b value factored out, and then you have x plus a number. All right, so that's the first step. So we can do this by factoring. And I'll show you that. Okay, so the original input for our function was 1/2 x plus 1. I need to rewrite it so it's of the form b times x plus h. So I can actually just artificially pull out a 1/2 from both terms. So it's 1/2 times x plus 2. All right, so this is now of the correct form. This is now of the form b times x plus h. So I hope everyone sees that. That's b, that's h. Okay.
But would that also be acceptable? I mean, since most computers will recognize it, or not really?
So it's not going to be this hard. I'm going to tell you like as a hint. You're going to need to rewrite it like this, and the reason why you have to is so we can apply our correct order from above.
Okay.
If you left it like this, the order that I presented to you, the order of transformations, would not work.
Okay.
Okay, so you need to rewrite it as b times x plus h. All right, and you can do that just by kind of factoring out a 1/2 from both terms here. So just convince yourself, if you distribute the 1/2 into this parenthesis, into the set of parentheses, you will get back the left side. Okay, so now we're good. Okay, so thus, our function takes the equivalent form. Okay, it takes the equivalent form f of 1/2 times x plus 2 minus 3. Okay, so I hope everyone realizes what has been done here. The function that was given to us was f of 1/2 x plus 1 minus 3. I just went in and rewrote the input of f, so it was of the correct form. So the 1/2 x plus 1 got replaced with 1/2 times x plus 2. And the minus 3 stayed. The reason why we do this is so we can apply the correct order of transformations. All right, so now let's do that. Okay, so using our order of transformations. We first, so if you just look back in your notes, or just like if I were to scroll up here, the first thing we do is horizontally stretch by 1 over b. Okay. We first horizontally stretch by 1 over, so what is b in this case? It's 1/2. So it's 1 over 1/2. So this is 2. Okay. So that's what you do first. And the picture is this. Okay, so here's the first transformation. Sorry, just give me a second. Right. Okay, so you can kind of see now, we did stretch horizontally by a factor of 2. So look at the original guy, it looks like this. We stretch it horizontally by 2. All right, so it got a little wider. That's the first thing. Okay, next, so now just following the order that I outlined above, next we horizontally shift. Horizontally shift left by 2 units. Okay, and it's to the left 2 because I have x plus 2. A plus 2 corresponds to a left shift by 2 units. All right, so what's the picture for that? It's this. All right, so I hope you guys can see, comparing this picture to that one, the only thing that changed was the graph was shifted to the left 2 units. Okay. Okay, and what's the last thing? And the last thing we got to do, so the last thing on that list, on the correct order of transformations, we vertically shift down by 3 units. Okay, and where does that come into play? You scroll up, it was -3. There was a -3 on the outside of the function. Okay, so that's why we vertically shift down by 3, and that will finally take us to the final picture of the graph. So, and there it is. All right, so I hope everyone sees that from here to here, this picture to this picture, the only thing that was done, it was a vertical shift down by 3 units. Okay, so that's how you need to approach these types of questions. You need to apply the transformations in the correct order and do them one at a time, and just take your time with them. Okay,